This is Math 372, Lecture 18. So what we're going to do today is we're going to do the Schwarz lemma, and we're going to talk about some of the consequences of the Schwarz lemma as to why do we care so much about proving this. And so I'm going to do things a little bit differently than I did last time and is in the book. I actually spent this morning doing the calculations on Mathematica, just so that if we do elect to go this route, I'm not going to get mistakes. And then after that, we're going to move on, and we're going to start talking about the Riemann mapping theorem. So this is one of the gems of complex analysis that says you have this conformal equivalence as long as you have a simply connected region that's not all the complex plane with the unit disk. The way you should view this is all we have to do is understand the unit disk. And if we understand the unit disk, we understand anything that's conformally equivalent to it. If you take it a topology class, you often see arguments like this. If you've taken probability, you often see this in terms of we only have a table of probabilities of the standard normal. And once we have that, we can get anything else. If you've seen logarithms, it's the most forgotten of the log laws, the change of base formula. The log of x base b is the log of x base c over the log of b base c. So if you know logarithms in one base, you know logarithms in all bases. So this is the motivation behind what we're doing. The purpose of the Schwarz lemma is going to help us uniquely classify what are the possible automorphisms of the disk. What can map the disk to itself conformally? And then once we have that knowledge, we can then extend that to knowledge of any other region directly. OK, so let me state the Schwarz lemma. And I will check my notes so that I either spell it correctly or spell it consistently from the last time. Because they're Schwarz with and without t's and whatnot in mathematics. So the Schwarz lemma. So f is holomorphic. F maps the disk to the disk, and f of 0 is 0. You should think of the last one, the f of 0 is 0, as a normalization. We've already seen examples of maps that are automorphisms of the unit disk that map alpha to 0 and 0 to alpha. So if we don't have a map that maps 0 to 0, just apply one of those maps first so we can assume we're in this case. All right. Then there are three things that are true. The first is for all z in the disk, f of z is less than or equal to the absolute value of z. Pretty sure that's the first one. Yes. 2, if there exists a z naught in D such that they're equal in absolute value, then f is a rotation. And the third one is f prime of 0 is less than or equal to 1 and is 1 in absolute value if and only if a rotation. OK. So here are the three statements. Some of them seems a little bit reasonable. So 2 coming from 1. Just very briefly, what would it mean if the absolute value of f of z naught equals z naught? What would be the consequence that you think we're going to get from this? The same distance from the origin. OK, they're the same distance from the origin. So what do you think that's going to mean for us? So we somehow want to get that f is a rotation. So what is a rotation? So a rotation will send z to e to the I theta times z. Another way of looking at this is f of z over z is always e to the I theta, which is constant. So for a lot of these problems, you want to figure out how should you interpret the statement. This is basically telling us this ratio is constant. And so if we know that it's constant, we have certain results that tell us when something is constant. What's the result that we know that will tell us when something is constant?
It's bounded.
If it's bounded, but on the entire plane. So this is not going to be bounded on. It's a good thing to go to. I mean, when in doubt, label is definitely one of the verbs to use. But it's not going to work here because we're only on the disk. When else will we know that something is bounded? Or when else will we know something is constant? So one thing is, if we know the function's bounded on the entire plane, it's constant. There's another thing we have where if something happens, then we must be constant.
When the derivative is 0?
Nope, that will only be locally, potentially. And in fact, you'll still have some variation around that, because if the derivative was 0 in a neighborhood, then by points of accumulation, the function would be identically 0. The other thing is, if it's a conformal map, we prove the derivative is never 0.
You try maximum.
So maximum modulus. So if you attain your maximum in an interior point, then you must be constant. And so this is trying to convince us that we want to study the function f of z over z. So maximum modulus. So I really want to try to emphasize how one gets to the arguments that are done in the book. The book often just goes boom, 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 boom. Why would we want to look at this? Why would we want to look at f of z over z? Well, if we know that f of 0 is 0, then f of z over z makes sense. It's a removable singularity. Right? We have that nice Riemann removable singularity theorem. F of z over z could be troublesome, but because f is holomorphic, f has a series expansion, it can't start off with a constant term because f of 0 is 0. So when we divide by z, this is fine. So we know g of z equals f of z over z is holomorphic. Do we know what g of 0 is? So do we know what f of 0 over 0 is? No. Maybe f of z is z to the 5th. Maybe it's 5z to the 5th. Maybe it's 10z to the 5th. Maybe it's just 2z or 3z. So we don't necessarily know what g of 0 is, but we know g of z is a holomorphic function, so g of 0 is well behaved. All right, so now let's look at proofs. Proof of 1. All right, so what we want to do now is we want to show that for all z, f of z is less than or equal to the absolute value of z. So let's consider g of z equals f of z over z. It's holomorphic on the disk. Where will this function take its largest value? On the boundary. Now, unfortunately, we don't necessarily know that our function is holomorphic on an extension to the boundary. We just know it's holomorphic inside the unit disk. So what we do is we basically just do a little technical bookkeeping. So here's a circle of radius 1. Here's a circle of radius r. If you want to think of r as 1 minus epsilon, where epsilon is going to 0. Inside this disk, the function is holomorphic. Inside this smaller disk, the function is also holomorphic, but we can extend it to the boundary. So on the disk dr, max on the boundary of dr. So we know g of z attains max on boundary of dr. So what does that mean? Well, g of z is just f of z over z, so we know that f of z will be less than or equal to z. Is that true? Do we know that? Can we immediately conclude, since it attains its maximum on the boundary, that f of z is less than or equal to z?
Well, that's assuming magnitude of g of z is less than or equal to 1.
Right. Do we know that the magnitude of g of z is less than or equal to 1? No. So we can't immediately conclude that. But we do know, because f maps the unit disk to the unit disk, we know f of z is less than or equal to 1. So we know on boundary, g of z is going to be less than or equal to 1 over r. Right? So because on the boundary, the absolute value of z is just r, and we know f is less than or equal to 1. The absolute value of f is less than or equal to 1 by assumption. Right? So now we can conclude that f of z is less than or equal to the absolute value of z divided by r for all r less than 1. Now we just replace, g of z is f of z over z, move z to the other side. And now what do we do? So we know this is true for all r less than 1. So now let r go to 1. So imagine f of z was greater than z. Eventually, this would fail for some r. So now we just take the limit. This is true for each r less than 1. It's true in the limit. We get f of z is strictly less than or equal to z. If this was a if this was a strict inequality here, it would become a less than or equal to here. Because when we take the limit, a less than can become a less than or equal to, but it can't become a greater. So if you're not convinced about this, put in a specific value. Put in f equals maybe 0.9 at z equals 0.899999999, something like that, man. And then when you take the limit, there will eventually be an r that will cause a contradiction. R will be eventually so close to 1 that this will fail. Okay, so this is the proof of the first part. So any questions on the first part? Okay, so we know that not only is f mapping the disk to the disk, but each point is not pushed further away from the origin than when you start. Right? That seems interesting. Right? There's lots of different maps I could have. And if I have a holomorphic map from the disk to the disk that fixes the origin, no point is pushed further away. Okay? So, again, you can always think about, real functions and try to come up with something that's different. So imagine f(xy) defined as follows. X, y, and now what I want to do is I want to just magnify it by a little bit. And so originally it was x squared plus y squared. That was how far away, or square root of x squared plus y squared was how far away it was. I want to make that a little bit larger, but still be less than 1. So I could do divided by, say, r of xy, where r of xy is the square root of x squared plus y squared. So that's how far we were. Now I look at how much we have left to get to the boundary and divide by 2. So that will push all the points out just a little bit. It will send 0 to 0. So this function f of 0, 0 is the point 0, 0. But it violates this condition. So what do you think must be true about the associated map? Not holomorphic. Or complex analysis is fundamentally on shaky foundations. All right? This late in the semester, I think we can accept the fact that we're pretty confident. So the real maps are very different. All right, so now we're saying the second consequence is imagine there was a point where they had the same value. Well, now this is just the maximum modulus principle. So now proof of 2. By maximum modulus, we know g of z, which is f of z over z, is constant. Right? So what would it mean for it to be constant? It has to equal some constant value. So we know f of z equals cz. So we have to just figure out what is the only possibility for C. Well, because these have the same magnitude, what can you tell me about C? Yeah, it has to have absolute value 1. And since C has absolute value 1, we can write it as e to the I theta for some theta. So it's nice to know that any number with absolute value 1 can be written in the form e to the I theta. This is now just a rotation. Because if I start off, if I go z to e to the I theta z, if we wrote z as r e to the I phi, we see we just add the angles. And we would get r e to the I theta plus b. So we would just be rotating by theta radians. OK, so this handles 1, this handles 2. All that's left now is 3. That if the first derivative at 0 has to be less than or equal to 1, and if it's 1 in absolute value, if and only if f is a rotation. Right. If it's a rotation, is the first derivative 1? OK, that part's not a problem. The harder part is to show that it must be less than or equal to 1 in absolute value. OK. So let's do proof of 3. All right. Want to show f prime of z, so f prime of 0 is less than or equal to 1 in absolute value. What would it mean if it was greater than 1 in absolute value? So there's a lot of different ways you can prove this. I'm deliberately not looking at my notes. I wanted to at least state the theorem correctly. I thought that was important. But I want to try to look at this live. So I can think of several different ways one could try to approach this. OK, so good. So where would that give us a contradiction? So we know that f of z is supposed to be strictly less than or equal to z. So if the first derivative is greater than 1, we're increasing by too much. All right, let's try to make that rigorous. So assume not. So then we can write f of z. We know the constant term is 0 because we're assuming f of 0 is 0. If we're assuming that it's greater than 1 in absolute value, I have to have a z term. Because if I don't have a z term, then the first derivative is 0, which is, last time I checked, less than or equal to 1 in absolute value. So it would have to be of the form, az plus, also a1z1 plus a2z squared plus yada, yada, yada. And the absolute value of a1 is greater than 1. Well, what this means is we can write f of z as a1z plus some function over here. I'll pull this out and write it as 1 plus h of z. And as z goes to 0, what does h of z go to? 0. I'm pulling out the z term over here. So this was a z squared, z cubed, z to the fourth becomes z squared, z cubed. Everything here is left with a power of z. So when I pull out an a1z, this one over here gives me this term, and then this over here is still going to have a z left. So note, h of z goes to 0 as z goes to 0. So if I now look at f of z over z, I get f of z over z is going to be a1 plus a1 h of z. And now as we send z to 0, this goes to 0, and in absolute value, this will be strictly greater than 1. So as z goes to 0, the absolute value of f of z over z converges to a1, absolute value of a1, which is greater than 1. Contradiction. So by using the Taylor series expansion, we were able to get this. The book might have a different proof. I like this idea of saying, well, what do we know? Locally, it's got to look like this. Here's the main term. Here's the error term. The error term is eventually so much smaller than the main term that it's dominated by this. So we've now shown that the first derivative is always less than or equal to 1, and now we need to show that it's 1 in absolute value if and only if it's a rotation. All right, so what would it mean then if the value was 1, it was not a rotation in absolute value?
Like the identity.
Well, so over here now, imagine that the first derivative is 1. So a1 would have to be now 1. Let's go through this argument and see what would happen if a1 was 1 in absolute value. We want to prove that it is a rotation. So what must be true about h of z? What would we want to show about h of z if a1 equals 1 in absolute value? H of z would have to be what for us? If we want it to be a rotation, what does a rotation look like?
Just A1 being some E to the I data and
Yeah, so what would the remaining part have to be if it's a rotation? 0. So if we want to show it's a rotation now we go through this argument, and now we assume a1 equals 1 in absolute value, and then we would have to show all of this is 0. Okay? So we can get down to this stage over here. So we now need to do the other part. So we're really close. So, okay. Assume a1 equals 1. Must show h of z is identically 0. We know that f of z over z is a1 plus a1 h of z. And we know h of z goes to 0. So if we can show h of z is constant, the only thing it can be is 0. Any thoughts as to how we could show h of z is constant? What do we know about complex maps? So we've used the maximum modulus principle today, but the maximum modulus principle had two friends. Or at least they were all in the same section. And they were given as the big three consequences of the argument principle. One was Rouchet, and the other one is the open mapping theorem. What does the open mapping theorem say? Maps are open, sets are open. We know H maps 0 to 0. So by open mapping, H of 0 equals 0. So if not constant, maps a open neighborhood of 0 to an open neighborhood of 0. All I have to do then is choose h of z to be real and positive. And then we will have pushed this by a scaling factor. So if you want, here's 0, here's some little open set, we apply h, here's 0 again, there's got to be something over here. So there's got to be some point, or some sequence of points that are hit here. And so choose z delta such that h of z delta is greater than 0. And now we get f of z delta over z delta is equal to 1 plus delta A1. And in absolute value now, that's greater than 1. And that's a contradiction. Okay, so I'm not sure which way the book chooses to prove these. I really like the idea of using the Taylor series expansion. Whenever we see holomorphic, we should be thinking analytic. I like using the open mapping theorem. Complex valued functions that are differentiable have very different properties than real valued functions. Whenever you're looking at problems, you should have a list of things to try, a list of things to think about. Can I use Rouchet? Can I use open mapping? Can I use maximum modulus? We saw for the problem about putting endpoints on the unit circle and finding a point whose product of the differences was 1. I would love to see a real variable proof of this here. Should there be one? And if there is one, is it a legitimate one? Or are you essentially reproving all of the results you need from complex analysis? But go through your list whenever you have problems like this. Okay, any questions on the proof of the Schwartz lemma? Right, so what I want to do is I want to leave the Schwartz lemma, the statement over here. I'll talk first about the consequences of this for understanding the unit disk. We will then migrate to the upper half plane. And then, if time permits, we'll talk a little bit about some of the stuff we're going to need for the proof of the Riemann mapping theorem. As a little bit of a teaser or precursor as to what's going to happen, what we will eventually be doing is we'll be looking at a sequence of functions that map set to the unit disk. The first thing we'll do is we'll say, without loss of generality, we can map our set inside the unit disk. So we might as well assume we have a map from a simply connected subset of the unit disk to the unit disk. And without loss of generality, we can adjust things so that 0 is mapped to 0. We know how to do this. And then what we're going to do is we're going to look at functions that are expanding in terms of their value of their derivative at the origin. And then we're going to take some kind of limit. And we're going to make an argument that that limit exists, and that limit is holomorphic, and that limit maps the unit disk to the unit disk, because if it didn't, we could have found something that would be a little bit bigger. And so this condition on the derivative is going to turn out to be very important. Okay, let's do some consequences. Out of curiosity, how many of you have seen Spaceballs? Right. I see some smiles, but all right. So here's a question. Enumerate all automorphisms of the unit disk. And again, we've already shown that if we can do this, we can enumerate all the automorphisms from any simply connected set that's not all of C, so long as we know the map from it to the unit disk. Right. We know these are really good functions. C alpha of Z is alpha minus Z over 1 minus alpha bar Z, where the absolute value of alpha is less than 1. So for any number in the complex plane, if its absolute value is less than 1, we can build a function like this. And we have two wonderful properties. C alpha of alpha is 0, and C alpha of 0 is alpha. So it just switches those 2 points. And C alpha composed with C alpha is the identity map. So it's its own inverse. And to, I guess, continue a Spaceballs joke, it's its own best friend. Anybody know which character? Oh, sad. Okay. Are there any other automorphisms you can think of the unit disk? Rotations. So we could do R of Z is e to the I theta Z. Theta is real. And we can compose automorphisms. Now, if I compose a bunch of C alphas, say I have C alpha 1 composed with C alpha 2 composed with C alpha 3 composed with C alpha 4, what kind of map is that?
Either C alpha or the,
I'm sorry?
it's either C alpha or it's either 2.
Well, so I'll have, C alpha 1, C alpha 2. So it's just some.
Oh, it's different.
Yeah, so what if I have C alpha 1 composed with C alpha 2, composed with C alpha 3, composed with C alpha n? Let's say I just have a bunch of them and I just iterate. What will I get?
Yeah, holomorphic function.
I'll get a holomorphic function. Any thoughts as to what kind of holomorphic function?
It would be just another, so it would just be a different C alpha.
Yeah.
Another alpha.
That maybe there should be some alpha such that the composition of these. So I'll leave that as something for you to ponder. That if we just keep iterating this. So if I now apply 0 is mapped to alpha n, and then seeing where all these different things are going. So do we think something like this is true, or do we think it's more complicated? If you were trying to understand this, what should you do first? Rather than doing alpha 1 through alpha n, just do 2 of them. And so if you looked at C alpha composed with C beta. Now, if I apply this to the point C beta of 0, let's see, C beta of C beta is just the identity, so this would just send it to alpha. So this is a map that sends 0 to alpha. I'm sorry, it sends C beta of 0 to alpha. So this maybe looks like it's the map C. So okay, so this would be, so this sends this to beta. That then sends it back to 0. This sends it to alpha. So this sends 0 to alpha. So maybe this map C alpha composed with C beta, if I had to conjecture, I might conjecture this would be C of C beta. Seems a real reasonable conjecture. Over here, if I take the point maybe C alpha n, C alpha n minus 1, that might tell you what point to guess.
What is C of beta without a subscript in the C?
Over here?
Yeah.
Oh, sorry. It should be C sub beta of 0. Thank you. Because that was the point that was sent to alpha. So, okay, so let's see.
That's just beta.
Right, so let's see if we're doing this right. So this sends, if we start off at this point, this, oh, okay. Right, so maybe I've done this one. All right, so let's see. We want to, right, so we want something that's going to go to 0, right? And we know alpha is sent to 0. So I'm sorry, I think it should be maybe C beta of alpha. Now when I apply this, I'll get alpha, and C alpha of alpha is 0. So I think I had the indices wrong, thank you. And so now if I apply this, maybe the map C alpha composed with C beta is just the map C evaluated at the point C beta of alpha. And that's good because it now involves both alpha and beta. So then this would be wrong up here, but you should hopefully be able to figure out how to fix it. And this is at least a conjecture. You can then try it. Another way to do this is to actually write down the matrix representation of these maps and work with the matrix representations. But if you play some of these games and say, well, look, these maps, all I really need to know to determine them is where does 0 go, and wherever 0 goes, that's what's sent to 0. Okay, so we've got about 10 minutes left. So we have these as some possible maps. We can compose them with each other. Well, a rotation with a rotation is a rotation. And so the question is there anything else other than these? And so the first thing is, well, if I have an automorphism of the unit disk, I might as well assume that 0 is sent to 0. Because if I'm trying to understand, I can always use one of these C alphas. So without loss of generality, enough to study automorphisms F from the disk to the disk such that f of 0 equals 0. Because if I had something else, more generally, if I have some G from the disk to the disk, look at G composed with C of alpha. And then that will send whatever point, because it's an automorphism, something goes to 0. And so I think the point would actually be G inverse of 0. What goes to 0? By definition, G inverse of 0. So now, if I apply this, hopefully I have things set up correctly. Probably do not have things set up correctly. So I think this is what I want. So now if I take 0, I apply G of 0. So maybe I just want G of 0 here. And so now if I look at this map, G of 0, then C G of 0, G of 0 will just be 0. So this now sends 0 to 0. So my F would be of this form. So if I can completely classify F, the way I would get G is then this would have to be one of those F. So G would have to be equal to C of G0 inverse composed with F. But the inverse is just itself. So I just have to understand the automorphisms from the disk to the disk that fix the origin. OK. Well, the Schwarz lemma has not been erased all day, right? We've been leaving it up there probably for a reason, right? If you look at it, that's our situation. We have a holomorphic map from the disk to the disk that fixes the origin. So we know f of z is less than or equal to z. We know if there exists some point such that that point and its iterate under f have the same absolute value, then g is a rotation. Because f maps the disk to the disk, what does f inverse do? It maps the disk to the disk. What does f inverse do to 0? And it's a holomorphic. So look at f and f inverse. Applying point 2 to f, we know f of z is less than or equal to z. We also know f inverse, I'll use some other point w, is less than or equal to
I was wondering how that
w. This is why I'm trying to go really slowly and try to motivate how one gets to these insights. Is we know f is a conformal map. We know f inverse is a conformal map. We know they both fix the origin, so we can apply 2 twice. What point w should we apply this at? Yeah, take w equals f of z. And now this is going to give us f inverse of f of z, which is just z, is less than or equal to f of z. But we know from this, it's less than or equal to z. So what do we know? Therefore, in fact, f of z is always equal to z in absolute value. Now use Schwartz 3.
So every conformal map from the disk to the disk is a rotation.
No, every conformal map that fixes the origin is a rotation.
Yeah.
So now because we have this, we know any map G is a rotation. So I might have things in the wrong order, but this gives us the full classification. Oh, no, no. So at this point now, we have to be just a rotation. Okay. So when the dust settles, after doing some of the algebra, let me see if I can get this to move. It's doing so well. So we get automorphism from the disk to the disk of the form e to the I theta alpha minus z over 1 minus alpha bar z, absolute value of alpha less than 1. Okay. Now, for a lot of problems, it's actually more convenient to look at the upper half plane. I just want to say, is the green light still on? Because it's not moving. It's not. Okay. 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 So hopefully no audio is lost. I'm speaking loud enough, it's okay. So all the maps from the unit disk to itself look like this. If they fix the origin, they'll just be a rotation, but more generally they look like this. The key insight was when we did the argument. One of those days. I did. You just there you go. Yeah. That seems to be working good. All right. So the key argument was we used Schwartz 2 to both f and f inverse. And we've got this beautiful chain z less equal to f of z less equal to z in absolute value by applying with f inverse, applying it to the point w plus f of z. We could look at what's going on with the upper half plane. And so if we have the upper half plane, we have some maps. So at this point, I think we can finally get rid of the Schwartz lemma. It did its job. So we have the upper half plane here, and we have the unit disk here, and we have maps. Oh well, thank you. We have maps f of z and g of z. So f of z, and I don't like how they're written. It's written as I minus z over I plus z, and then g of z, well, I guess I can do g of w, is equal to I, and then it's 1 minus w over 1 plus w. Thank you. So remember, if we're writing these in matrix form, we would write this as negative z plus I over z plus I. Then this would correspond to the matrix negative 1, I, 1, I. And if you act that on z, you get negative z plus I over z plus I. And so you would have to similarly write something like that over there. So the claim is the automorphisms from the upper half plane to upper half plane are of the form A, B, C, D, acting on Z, which is AZ plus B over CZ plus D, where AD minus BC equals 1, AB, CD are real. Okay. Now, one of the things we have to be careful about and remember is that when we look at these matrix representations, the identity matrix, so let's see this will work. Now it's working. Excellent. So if we look at these matrices, the identity matrix, 1, 0, 0, 1, sends z to z plus 0 over 0z plus 1 is z. But if I choose any d, 0, 0, d, acting on z, it goes to dz plus 0 over 0z plus d is also z. So there's an indeterminacy. If you've seen anything with projective geometry, you can basically mod out by all multiples of the identity matrix. They all have the same action. So the book goes through a proof that this is that these are all the automorphisms. And if there's anything else, it's basically equivalent to this by just multiplying by a matrix like this. Okay. Is there any way we can see this, or at least see that it's reasonable? How large is this space of matrices? How many parameters do we have for the space of matrices? Three-dimensional. So this is a three-dimensional space over the reals. Because once you specify A, B, and C, then D is fixed. Let's look at what's going on in what I had just erased. All right, so we had the e to the I theta, alpha minus z over 1 minus alpha bar z. How many parameters do we have here? Why 2? Okay, what kind of number is theta? It's real. What kind of number is alpha? Alpha's complex. So we have 3 real parameters here. Now again, alpha has to be numbers of absolute value 1. I'm sorry, absolute value at less than 1. So if you write alpha as alpha x plus I alpha y, alpha x squared plus alpha y squared is strictly less than 1. But it's still, you have 3 free parameters. So you have 3 real parameters. So it's at least reasonable that the spaces could be the same. You at least have the same amount of freedom. So what I did, and I will send you the Mathematica code, is I actually wrote down what the different maps would be in these matrix forms. And I said, well, look, I know the maps between the upper half plane and the unit disk. I know what the automorphisms look like on the unit disk. So if I want an automorphism on the upper half plane, I start on the upper half plane, I map to the disk, I do an automorphism on the disk. This is my e to the I theta, c alpha z. And then I come back. And then I look and see what comes out. And I got a lot of gobbledygook. And then what I did is I noticed that every factor in the matrix that came out was multiplied by a common value, which was non-zero. Okay, if I multiply all the values by that, I'm changing the numerator and the denominator of the fractional linear transform by the same thing. I multiply 5, 5, 5, 5. That does nothing. So I could remove that factor. Then I got a matrix whose determinant was not 1. Its determinant was, I think, 4 minus r squared. No, I'm sorry, 4 minus 4 times r squared, where r was the length of alpha. Well, since r is less than 1, 4 minus 4r squared is less than 1, I can rescale by one of these diagonal matrices so that my new matrix has determinant 1. So at the end of the day, I was able to convert and take an automorphism of the unit disk and get it to be of the desired form here. And you can check and see that all the stuff here clearly have the property of mapping the upper half plane conformally to the upper half plane. And so this is a full enumeration. And we don't have to go through the book's argument. Because we understand the unit disk, we can pass from that knowledge to the upper half plane. Conversely, you could study the upper half plane and then pass from that knowledge to the unit disk. So this is a good place to stop for today. I will send the Mathematica code. It's good to be able to do simple calculations like this. And then we will start the Riemann mapping theorem in detail on Wednesday. Make sure you are familiar with things such as uniform continuity and uniform convergence and Cantor's diagonal argument.